Hey folks, today's topic is the tangent line problem, kind of the cornerstone of all of, well, at least differential calculus. So it's this idea that if I want to figure out the slope, I usually need 2 points. I'm trying to pick a color here. All right, let's go with, all right, so here's we got our function. F of x equals 3x minus x squared. How fast is the graph changing at x equals 1? In other words, what is the slope of the tangent line at x equals 1? Well, I go up here, I trace along I have an x value of 1, gives me a y value of 2. Now, that's the location of that point. That's the location. We want to figure out how fast is that thing changing at that point. A similar problem, simplified problem, equivalent problem would be, I know where the baseball is right before it hits my face. The question is, how fast is it going when it's hitting my face? That's what I want to know, right? I know that it's going to hit me. I want to know how fast it's going, and that's the question here. I know that this point is at a height of 1. I want to know how fast it's going. Okay, well, that means that's the slope. Rate of change and slope now should be interchangeable phrases for us. So this thing called the tangent line is this line that hits only this point on the curve. Now, that's a little bit of a misnomer, and I'll talk more about it later. But that's the idea. This is what we call the tangent line. And what we want to figure out about the tangent line is the slope of that tangent line. Okay, well, let's go back to Algebra 1. We've done slope for a long time. How do we figure out what the slope is? Oh, crap. What's that formula for slope again? Slope is equal to y2 minus y1 over x2 minus x1. So this was all fine and dandy back in Algebra 1 because what were we given? 2 points. And in this case, if you look, the only point that we know that this line goes through is the point 1 comma 2, and we need that second point. And so this is where you come in, this is where the calculus comes in to save the day here. So I'm going to go to a visual, and hopefully this kind of makes sense. So here's the point. I just picked some random point. Unfortunately, I can't change the function. I wanted to change my function, but I couldn't get it to change. So, anyway. So I want to figure out here in purple here is the tangent line. I want to figure out the slope of the tangent line. Problem is I don't have 2 points. So what we do instead is we go with this thing called the secant line. So what we've done is we've started at 1 and we've gone some distance away. We call that distance h or delta x. I think if you have Roop, I think he calls it delta x. It's some change in x. Delta x means change in x. Now, the farther you are away, the bigger that delta x is, the bigger the h value is, the worse that slope is. Look at the blue line in comparison to the purple line. It's much worse the farther away we get. But as we get closer, as we make delta x smaller and smaller and smaller, look what's happening to that blue line. Until we get that h to be 0. Oh, there it is. Until we get that h to be 0. And then the tangent line and what are called the secant line is the same line. But we still have this problem. We only have 1 point. So how do we solve this? Well, this is where our good friend the limit comes in. What I can do is I can calculate the slope of the blue line, the secant line. I can calculate the slope of the secant line a little bit closer, the slope of the secant line a little bit closer, and 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 then I can and then super close. And what I can do is I can then use that limit to predict where these slopes are going, where these numbers are going. And eventually that limit would take me right back to the slope of the tangent line. And that's what Corpy has us do here. He has us start off by saying, all right, so we want to figure out the slope of the tangent line. Use your calculator, evaluate the average rates of change, the slopes between the points 1 and f of 1 and the following points, and be sure to show the difference quotient. So let's talk a little bit about that difference quotient. You have to get used to the way this is written. I don't know what to tell you. I know this makes a lot more sense, but this is not how fancy math people talk. The way we write it up now is we say m equals, and what do we call y values now that we're in advanced math? We don't call them y values anymore. We call them function values. So this function value is dependent on what x value? On this x value x2. So this is called f of x2. Minus, and then this y value is dependent on this x value. We call that f of x1 over x2 minus x1. And maybe it's just me. I'm intimidated when I first saw this. This threw me for a loop, but it's no big deal. Maybe you get it and you're fine. But these just mean the function values at these x values. What is the function value at these x values? Okay, so you're going to see some phrases that we're going to use a lot in this class. You have to identify that these really mean slope. Average rate of change. That already means slope. That's the slope, that's the slope, that's the slope. Now that's the slope of the secant line, so that's this formula. Whenever we want to figure out the average rate of change, average rate of change, we're going to start to call that AROC. Average rate of change. So when you see that phrase, average rate of change, it means what's happening between 2 points. There's another phrase that we're going to use. It's called instantaneous rate of change, and that's saying what's happening at specifically 1 point. So I should probably go back up here and rewrite this. We don't really write them as 1 comma 2 anymore. We would say f of 1 equals 2. That's a much more succinct way, much more mathematical way of saying this. Okay, so let's go ahead now. We're supposed to just calculate some slopes. That's very doable. We're supposed to calculate the slope between 1, f of 1 equals 2, between that point and these points down here. So at 1.5, f of 1.5, so let's see, 1.5, track up here. I'm going to say it's probably the vertex. I play connect the dots. What's this thing called again? This is called a secant line. Oops, that's called a secant line. So let's calculate that slope now. So that would be f of 1.5 subtract. So I'd go from the further point back to the original point. F of 1 over 1.5 minus 1. Okay, what do you think that is? It's not 2.5, probably 2.25, let's say. It's halfway up there. So this would be 2.25 for my y value, my function value, sorry. Minus, I know this one is supposed to be 2. Oh, how could we find that out exactly? I shouldn't have just guessed and checked. How could we find that out exactly? We could plug and chug, right? We could plug this. We're allowed to use our calculator. So let's just double check. What is f of 1.5? So that would be 3 times 1.5 minus 1.5 squared. Okay, good, 2.25. Let's just double check 1 while we're at it. Yep, okay. So 2.25 minus 2 divided by 1.5 minus 1. We get 0.5, which is 1/2. Okay, now we're going to figure out what is the slope at between 1 and 1.1. All right, so here's 1. 1.1 maybe is something like this. Oh boy, I'm going to run out of room here pretty quick. That's 1.5, so it should be about 1/5 of the way. I play connect the dots. I'm not going to go as far because I don't want to run into that word tangent line. This is what again? This is called a secant line. They said we're allowed to use our calc. So this is f of 1.1 minus f of 1 over 1.1 minus 1. Second enter, second enter, second enter. Change these, insert a 1 in there, so it's 1.1. So we get 2.09. 2.09 minus 2 over 1.1 minus 1, which now I'm going to calc 2.09 minus 2 over 1 point, why didn't I do that in my head? 0.9, so we get, wait, 0.9? Oh, yeah. 0.9. I'm going to let you try to do the next two. You don't need to draw the tangent line, or the secant lines, I'm sorry, because it just gets continually closer and closer. As you can see, go from the pink line to the green line is getting closer to the purple line. Using your calc, let's see if you can calculate the slopes, the average rate of change between those y values, or those two function values. Pause it if you haven't yet. Pause it. Try it on your own. Come on. Anybody want to make a prediction? If we went to 1.0001, put another 0 in here, or anybody want to make a guess what would happen here? All right. So based on your mathematical evidence from up above, we don't have anything, we haven't done a proof yet, but this is our basic idea. Based on this evidence, how fast is the graph of f of x changing at x equals 1? That is, what is the slope of the tangent line? So if I gave you a table and I had it go 0.5 to 0.9 to 0.99 to 0.999, what would you guess we're headed towards? Hopefully you're guessing that our estimate, what do we think the slope of the tangent line at x equals 1 is 1. That would be my guess. Okay, so hopefully that gives you kind of the basic idea of what we're doing. Now we're going to try to do this algebraically. So I don't want to have to do this every single time. I don't want to have to keep plugging in all these values. I want to be able to do this algebraically. And that's what we're talking about here. Find the average rate of change. Boom. Highlight it. Average rate of AROC. Average rate of change is always, always, always the slope. AROC is equal to slope. Between these 2 points where h is the change in x between our two x values, and then simplify your function a of h. So they asked us to name the function a of h. So a of h is equal to the rate of change function, which just means slope, between these 2 points. So I'd take y2 minus y1 over x2 minus x1. So that would be f of 1 plus h minus f of 1 over 1 plus h minus 1. So let's talk about how we would now clean this up. We would take this thing and we could now, actually, not yet. So let's now think about what is f of 1 is easy to calculate. What does f of 1 mean? What do I do with the f function if it says f of 1? Well, I plug in 1 for x and I figure out what I get. What does f of 1 plus h mean? The exact same thing. So instead of plugging in 1, I'm going to plug in 1 plus h into my function. So that's going to be 3. I'm going to grab a different color here to highlight this. 3 times 1 plus h minus 1 plus h squared minus, and then I'm going to plug in 1 into these things, minus 3 times 1 plus 1 squared. Now, why did that turn into a plus? Hold on a minute here. I thought the formula was subtract. That's because I thought the formula was 3x minus x squared. Why did this turn into a plus? Because I'm subtracting that group, and that's something you're always going to want to do. Switch the signs of this back term. So this is going to turn into a minus 3. That's going to turn into a plus x squared. All over. Now look down here. What do you notice? 1 minus 1 cancels, and we're just left with h. Okay, so now we can start to clean this thing up. 3 times 1 plus h, I would just distribute. That'd be 3 plus 3h. Now this gets a little bit sticky. 1 plus h squared. I wish I could just square both of them, but I cannot. Instead, what I need to do is expand them. So I'm going to go over to the corner of my paper, and I'm going to practice review expanding 1 plus h squared. So 1 plus h squared is the same as 1 plus h and 1 plus h. Then I would start to distribute. 1 times 1 is 1, plus an h, plus another h, plus h squared. 1 plus h is 2h plus h squared. We're going to call this a 1, 2, 1. That means when I have my coefficients like this, it's 1 times this. Actually, I'm going to do it up at the top. I'm going to explain this one time, and then I don't have to explain it again. So I can just reference this. So if I want to take, let's do x plus h squared. That turns out to be x plus h times x plus h, which turns out to be x squared plus xh plus xh plus h squared, which combining like terms gives me x squared plus 2xh plus h squared. I'm going to call this a 1, 2, 1. The coefficients are 1, 2, 1, and then I want you to memorize that the first term gets squared, x times itself, x times x goes here. Then you're going to do x times h, you're going to times them by each other, and that's going to happen twice. That's why it's 2 of those. And then you're going to get 1, h times h, which is h squared. This is called a 1, 2, 1. So what this down here, what I would do here, this is a 1, 2, 1 with a negative out in front. So that's going to be a negative 1, negative 2, negative 1 when this gets distributed to this group. So if I come back to this problem, this is the expansion of 1 plus h squared, and then I'm going to times everything by a negative. Negative 1, negative 2h, subtract, I shouldn't say negative, I should say subtract. Subtract h squared. And then minus 3 times 1 is 3, plus 1. All over h. Now we can start to clean this up, and you should notice a bunch of stuff happening at this point. Things should cancel. Everything without an h should cancel at this spot. 3 minus 3, negative 1 plus 1. Now I'm just going to cancel a little bit at a time because this is the first time we're going through. In the future, we're going to cancel more. Okay, now that I've canceled everything without an h, that means everything left has an h, which means I can kill an h from every single piece. Oh, I guess I could have combined those. I'm going to cancel h's at this spot. 1h there, 1h there, 1h there for that 1h there, which leaves us with, what's 3 take away 2? 1 minus h. This is my function, so therefore a of h equals 1 minus h. So what happens to the secant lines between the points 1, f of 1, and 1 plus h? Okay, let's talk about what this means. This means that you're starting at 1, you're going just some distance away, some small distance away. We don't want to go super far away because you might run into some asymptotes or some holes or holy jumps or jumps. We just go very, very, very small distance away from 1. And then we take that very, very small distance away from 1 and we make that distance smaller and smaller and smaller, just like we did here. Corpy went from 1 to 1.5, and then he made that distance get smaller and smaller and smaller. That's the idea of the limit. So this is the function of what happens for h. What happens as h heads off to 0? What is happening to the secant? What is happening as h gets smaller and smaller? The secant lines are approaching the tangent line. So the secant lines are getting closer and closer and closer to becoming the tangent line. So then what we do is we evaluate that final distance. What would happen then if I evaluate the limit of a of h as h approaches 0? So the limit of 1 minus h, I'm going to write it out like this. The limit of a of h as h approaches 0 is equal to the limit of 1 minus h as h approaches 0, right? That's what my function is. That's what a of h is 1 minus h. Now I can direct substitute. I'm running out of colors here. I can direct substitute 0, never not first, and I get 1. Now, remember, this function here is the same as what he started off with here. And what did we predict the limit would be as we got closer and closer and closer to f of 1? We predicted that it would end up being 1. And algebraically, this is algebraically exactly the same thing that we did here graphically. We just don't want to have to graph this thing every single time. We want to learn how to do it algebraically. And so this was a specific example for 3x, the function 3x subtract x squared. We want to do this now for a general function f that we don't know what the actual equation is, and we get this thing called the derivative by definition. So there's two things that I want to talk about. The first thing I want to talk about is called the difference quotient. The difference quotient is f of x plus h minus f of x all over h. That's the same thing. Remember when we did that up here? This thing right here, this is what we call the difference quotient. Okay, the difference quotient is just the slope formula. Slope formula using f of x instead of y. So when I say the difference quotient, that's just the slope formula. Y minus y over x minus x. Well, wait, what happened to the x's on the bottom? Remember, it's x plus h minus x. X plus h minus x on the bottom. What's going to happen to those x's? Those are going to cancel out, and you're just going to be left with h. And then this thing that we call the slope of the tangent line is also called the derivative. The derivative is how fast the graph is changing at one specific point. And we call that the derivative. The derivative by definition. All right, so we use the symbol F with a little tick mark. That's read F prime. F prime means the derivative. That's telling you how fast, it's basically telling you what's the slope of the tangent line. How fast is the curve changing at one specific point? At an instantaneous, not an average rate of change, an instantaneous. The average rate of change is what we calculated here. But then what did we do to that h value? We eventually made that h value so small that we couldn't tell the difference between the secant line and the tangent line, and we got this thing called the derivative. So the derivative, by definition, the derivative essentially is a limit as h gets closer and closer to 0 of the slope formula. Our slope formula is this thing right here, f of x plus h minus f of x all over h. This is worth memorizing. This is worth memorizing. I'm actually going to put a box around it with some stars. Those are not very good stars, but we'll have to live with it. Yeah, okay. Okay, let's see if we can get a couple of examples. Maybe we can finish this next one before the hour ends. So we now have an official thing, the derivative. If f is a differentiable function, that just means that you're allowed to derive it. We're going to talk a lot more about what that means in the next couple lessons. Its derivative function, which we write as f with this little tick mark, we call that f prime, is defined to be f of x equals the limit definition of the derivative. F prime of x equals the limit as h approaches 0 of f of x plus h minus f of x all over h. Seems complicated, seems scary, but it's not that bad once you get into it. Okay, just to point out other notation for f prime, you're going to see f prime, you're going to see y prime, and then you're going to see this notation called dy over dx. All those things just mean the derivative. All right, describe what okay, here's our function, f of x equals root x minus 2, graph f of x. So I'll give you a second here. I'm going to encourage you to pause. You should be able to sketch this without me giving you a hint. All right, what family are we talking about? Square root family. Are there any shifts? Yes, one. We're shifting in the x direction. So here's my first value. And what can you tell me about the family of square roots? You kind of go like a sideways parabola, something like that. Describe what the y values are doing and how they are doing it. Well, I would say that the y values are increasing, but over time, what would you say is happening to the increase of those y values? They're still always going up, but the going up part is actually slowing down a little bit. We're going to talk about that. That's going to be something called the second derivative that we'll get into. But the y values are increasing, but their increase is decreasing. All right, so let's go ahead. Now, find f prime using the limit definition of the derivative. That's what this is up here. That's the derivative by definition. So those of you who did the work in the spring, this will be a lot easier. For those who didn't, I'm talking to this is dating back to the COVID people, so hopefully since then we haven't had to be separated in school like that. So f prime of x equals the limit as h approaches 0 of, okay, so it starts off with f of x plus h. That means in my function, everywhere there's an x, I'm going to replace that with x plus h. So I would have x plus h minus 2 underneath the square root minus the function itself, which is square root of x minus 2 all over h. So what I did was I took out the x and replaced it with x plus h in the first piece. And the last piece, I just subtracted the function itself, and it's always over h. Now, what should we try to do first? Never not first is what? Plug in 0. So when I plug in 0, I get root x minus 2 minus root x minus 2 over 0, which is 0 over 0. So when I direct substitute, I get 0 over 0, which means there's a hole, and now we got to figure out where that hole is. So let's think back. Your math voice should recognize this. How do we handle these roots? What's the move that we're going to do to get rid of the roots on the top? Hopefully your math voice said conjugates. So I'm going to multiply by x plus h minus 2 under a root plus root x minus 2. Remember, the conjugate is first piece the same, second piece the same, middle switches. What that's going to do, it's going to make a difference of perfect squares when you're done with it, which means that the middle part's going to cancel out and we shouldn't have any roots anymore. Now, whatever you do to the top, you got to do the same thing to the bottom. A lot of kids forget this and they times the bottom by h. That is not legal. You got to keep this fraction still worth the same amount. Okay, now we can start to distribute. Now look, you haven't plugged in 0 for h yet, so you got to keep writing limit until you do. All right, so we're going to do this times this. Root x plus h minus 2 times root x plus h minus 2 is x plus h minus 2. Then the beauty of the conjugate is this thing times this thing is going to be some crazy root, but it's going to be a positive crazy root. Then when I distribute the next step, it's going to be the negative of that crazy root, so that part will cancel out. Now the trick here, the thing you got to be alert for, root x minus 2 times root x minus 2 is x minus 2. But what's a positive times a negative? Negative. So you've got to remember to distribute that negative as you go through. Minus x plus 2 all over. Now, a quick check is to make sure that everything without an h, everything without an h is going to cancel. That's a sign that you probably did things correctly. If you didn't have stuff canceling, you're in trouble. All right, now the bottom becomes a lot messier. It's a good trade, though. Believe it or not, it is a good trade. Okay, so now look at what's happening in the numerator. What's x minus x? Gone. What's negative 2 plus 2? Gone. And if you want to, at this point, you can cancel out the h's. I'm going to write it out with a little bit more detail because this is the first time that you guys, well, maybe the first time you've seen something like this. H over h times the quantity x plus h minus 2 plus x minus 2. Now, what do you notice happens with those h's? They gone. H over h cancels. That's the beauty of this. Because now, once we've killed that h on the bottom, we can direct substitute 0 in for that h, and we're left with 1 over. And I'm going to put a 0 in here, so I have root x minus 2 plus root x minus 2, which is 2 root x minus 2s. Yes, there's a root on the bottom. No, I'm not going to clean it up. You could if you want to. Nobody expects you to at this level. They have the sort of philosophy, if you can't clean something like that up, you shouldn't be in this class. All right, now, what's nice about this, the beauty of this, is now we've gotten the formula for all the derivatives of this function. So what's the slope of f at x equals 6? Well, what I can do now is mathematically what's that saying is, what is f prime of 6? And we can now figure that out because we now have a function for f prime. So I can take 6 and I can plug it into this. 6 minus 2 is 4. Square root of 4 is 2. 2 times 2 is 4. So the slope of the tangent line of my function at x equals 6 is 1/4. So all I did was plug it in to my function. Maybe I should write that out. I'll write that out just for the first one. I'm not going to write it out for any other ones. So what I did here was I plugged in 1 over 2 square root of 6 minus 2. All right, I'm going to encourage you to pause here and try to do the next ones on your own. Let's see how you did. 16 minus 2 is 14, so f prime of 16 would be 1 over 2 root 14. If this was a multiple choice question, they would expect you to clean that up. If it's a free response like this, I would not bother to clean it up. You can if you want to. Of 27, so f prime of 27 is equal to 27 minus 2 is 25. That's 5. That's 10, 1/10. And then last but not least, plug in 2. 2 minus 2 is 0. Uh-oh. 2 minus 2 is 0. 0 times 2 is 0. That's a 0 on the bottom. So f prime of 2 is equal to 1 over 0, which equals DNE. Describe the values of x for which f is continuous. Now, that doesn't have anything to do with the derivative, so let's go back up here. Do we have any problems with the square root family? Yeah, we do. We can't square root a negative. So any numbers that you plug in for x that cause a negative aren't included. So everything back here is bad. Everything from 2 and on is good. So we would say f is continuous on 2 to infinity, including the 2. F is differentiable. Okay, look at these 6, 16, 27. All of these points are differentiable. And the way you can tell differentiability is if there's any, we call them sharp turns, if there's anything weird happening. The only thing weird that's happening here, look at what the tangent line would have to be. So here's my, I'm trying to find a, I don't know if that works very well, but here's my tangent line. Then as my tangent line gets here, look what's happening to the slopes of my tangent line. All right, no big deal. I can figure out what those slopes are. But as we get closer to 2, what's happening to the slope of my tangent line? Eventually, it gets to this spot here where it goes perfectly vertical. So we're not allowed to differentiate what's happening at that point. So we would say f is differentiable on, it's still 2 to infinity, but this time the 2 is not included. This time the 2 is not included because at that point, strange things happen. So I wish I would have used the same color here, but I didn't, and we're going to have to live with that for the rest of our lives. Okay, last but not least, write the equation of the tangent. Boom! This is huge, huge, huge. We talk about this all the time. This happens over and over and over. The equation of the tangent line, the equation of the tangent line, the equation of the tangent line. You need two things. You need a point, and you need the slope. Over and over and over again. You need the point, you need the slope. To get the equation of a tangent line, to get the equation of any line, you need the point, you need the slope. Well, the point, how would we figure out the point? Well, the point is given to us by an x value and a y value. So my point is 27, comma, and then how would I figure out my y value? I would take that and I would plug it in. So I'd take 27, I'd plug it into my function. What's 27 take away 2? 25. What's the square root of 25? 5. So I find the point by plugging in my x value. If x equals 27, y equals question mark. The slope is found by this thing called the derivative, which was all this work that we did up to this point. The slope, m, is equal to the derivative at x equals 27, which we figured out to be 1/10. Now we can write our slope or our equation in any form that you want. They asked for Taylor form, so we're going to go for Taylor form. I would say Taylor form is point slope form with the number bumped to the other side. So it's y equals, it's supposed to be y minus 5, so that bumps over to be a 5, plus the slope, which is 1/10, times the quantity of x subtract 27. If you don't have Taylor form memorized, I'll write it up here one time, but you need to memorize it. We write so many equations. Taylor form is y equals, let's do it like this. Y equals y1 plus m times the quantity x minus x1. That's worth memorizing. Okay, folks, I think I'm going to stop here, and we'll pick it up. 3 pages, not bad. We'll pick it up next time.